Welcome to our quantum deep dive. Today we're plunging into the incredibly fascinating world of the top quark.
That's right. And our guide for this is a really insightful essay by Yorgos Napat. It's titled Top Quarks, Schlüsselteil der Quantentechnologie.
Which means something like top quarks, key components of quantum technology. Yeah.
Exactly.
So our mission today is to really unpack this. What is a top quark? Why is it so interesting? And maybe the biggest question, how can something that, well, basically vanishes instantly, how can that be relevant for quantum tech?
Right. Let's get straight to it. The essay frames top quarks as, fundamental building blocks, part of that quark family in the Standard Model.
So core ingredients of matter.
Core ingredients. They have that plus 23 electric charge, like up in charm quarks. But the thing that really makes the top stand out
is the mass. It's just so heavy. The heaviest quark we know.
By far. Absolutely. Yeah. And that extreme mass leads to a very, very strange life. It decays, well, incredibly quickly.
How quick are we talking?
The number is something like 5 times 10 to the minus 25 seconds.
Wow. 5 with 24 zeros after the decimal point. That's... Yeah. I can't even picture that. It's gone before light could cross an atom, basically.
Exactly. And the essay points out this is crucial. It means the top quark decays before it can do what other quarks do, form hadrons, like protons or neutrons.
So it doesn't get bundled up.
Right. And that means we get this unique window. We can study the top quark almost naked, you could say. We see its pure quantum behavior at these incredibly short times without the messiness of hadronization.
Okay, so it was predicted back in the 70s, I think. But finding it was tough because of that mass and short life.
Precisely. You needed accelerators with enough punch to actually create something that heavy. The discovery, it finally happened in 1995 at Fermilab using the Tevatron.
And that mass again, 173 GD squared, the essay says, which is like roughly the mass of a gold atom for one particle.
It's astounding, isn't it? A single fundamental particle weighing as much as an entire atom. And yeah, it's a fermion, spin 12. Like the other quarks.
And it usually decays into, what was it, a W boson and a bottom quark?
That's its main rat out, yeah. T goes to W plus B.
But let's really dig into that mass. The essay stresses it's more than just being heavy. Why is it so important for physics?
Okay, yeah, this is key. Its huge mass means it has the strongest connection, the strongest coupling to the Higgs boson.
The particle or field that gives everything else mass.
Exactly. So the top is like the ultimate test subject for understanding how that Higgs mechanism actually works, how particles get their mass.
And there was something else too, about the universe's stability.
Right. Its specific mass value is weirdly important for theories about the stability of the Higgs field's vacuum state.
You mean like, is the universe fundamentally stable in the long run?
Kind of, yeah. It's about whether our current vacuum state is the true lowest energy state or just a temporary low point. Some theories suggest that if the top mass were slightly different, our vacuum might be only metastable.
Which implies?
What?
A potential change, eventually.
Potentially. Though we're talking truly astronomical timescales, probably. But yes, a fundamental shift is theoretically possible depending on these precise values. It's mind-bending.
So this tiny particle's mass hints at the fate of the cosmos.
Wow. And there's more. Its mass and strong Higgs coupling also make it a prime hunting ground for new physics. Physics beyond the Standard Model.
Like supersymmetry or dark matter connections.
Exactly. Theories like supersymmetry predict partner particles, maybe even a stop quark partner for the top. Other ideas link the top or particles interacting with it to dark matter. So experiments at the LHC, they're looking really closely at top production and decay, searching for tiny anomalies. Deviations that could signal these new particles or forces.
And even though they vanish instantly, we can detect them at the LHC with experiments like ATLAS and CMS.
Yeah, absolutely. You don't see the top itself, it's long gone, but you see its decay products, the bottom quark jet, the stuff the W boson turns into. Physicists are like particle detectives, reconstructing the scene to prove a top quark must have been there.
Okay, right. Which brings us to that really intriguing bit in the essay. How can this incredibly fleeting thing possibly matter for quantum technology? That seems like a huge leap. Quantum tech feels like it needs stability.
It does seem counterintuitive, doesn't it? But the essay argues that top quarks, for that instant they exist, are pure quantum objects. They obey quantum rules, they can be in superposition.
And because they don't hadronize, we see that pure quantum behavior directly. At timescales we just can't access otherwise.
Exactly. So no, you're probably not building a qubit from a top quark. But studying its behavior, its dynamics in these extreme conditions, that could teach us fundamental things things that might inspire new quantum approaches.
Like the potential applications mentioned. They seem mostly theoretical for now.
Mostly, yes, but potentially very powerful, like high-precision sensors. Maybe studying top quarks helps us probe quantum fluctuations at super short times, maybe even vacuum fluctuations that could lead to new sensing techniques down the line.
Or simulating extreme quantum states.
Right. Making tops and colliders lets us study quantum field theory in regimes we can't easily replicate. Understanding these extreme states might be crucial for developing better quantum models, maybe even simulation techniques.
And the quantum computing link. The essay sounded cautious there.
It is cautious. It's not about standard qubits needing stability. But the suggestion is maybe the TOPS dynamics, its super fast evolution, could inspire different kinds of quantum processing. Things based on non-equilibrium states, maybe exploiting the fleeting nature instead of fighting it.
And what about the strong force, QCD?
That's another theoretical angle. QCD, the theory of quarks and gluons, is incredibly complex. Some ideas, especially around topological quantum computing, which have deep links to quantum field theories, might draw insights from how QCD behaves at these high energies, involving tops. It's speculative, like the essay says, but it connects particle physics theory to quantum information ideas.
Okay, here's the part that really bends my mind. Quantum entanglement. The essay says top-anti-top pairs can be entangled.
Yes. It's amazing. When you create a top and its antiparticle together, their quantum properties, like their spins, can be linked, entangled.
So you can test entanglement, a core quantum feature in this totally wild, high-energy collision environment.
That's the opportunity. It's a completely different regime from photons or trapped ions, testing quantum mechanics at its most fundamental, in the most extreme conditions.
But detecting it must be insanely hard. They decay so fast, and there's all this other stuff flying around.
Oh, it's a huge challenge, trying to see the subtle correlations in the decay products that prove the original entanglement. It's tough. But the essay does mention researchers are starting to see the first hints, signs of quantum coherence persisting in the decay patterns. It suggests we can probe these effects.
So, despite all we're learning, what are the big open questions? The essay mentioned some mysteries still surrounding the top.
Well, a major one is the potential link to dark matter. Are tops involved somehow? Some theories, like supersymmetry, predict top partners stop quarks that might interact with dark matter. Or maybe tops could decay into dark matter particles in some exotic scenarios, or act as a sort of bridge. The LHC is actively looking for any clues.
And its role way back in the early universe. Cosmology.
Yeah, the essay highlights that because it's so massive, the top was really important right after the Big Bang, in that super hot quark-gluon plasma phase. As the universe cooled, tops likely played a big role when the Higgs field kind of settled into place, influencing how fundamental symmetries were broken.
Which connects to that massive puzzle. Why is there more matter than antimatter? Barogenesis.
One of the biggest questions in cosmology. And yes, could tops be involved? Theories explore if processes involving top quarks might violate certain symmetries, CP symmetry, in a way that favored matter surviving over antimatter in the early moments. Its huge mass makes it a good candidate for potentially driving such effects.
So its brief existence might be tied to why we exist.
It's a very active line of thought, yeah, both theoretical and experimental.
But we still come back to that main hurdle for actual tech applications, that incredibly short lifetime.
Absolutely. The essay is clear on that. Direct manipulation. Probably not feasible with anything we can imagine now.
But studying it is still vital.
Definitely. Its unique quantum nature pushes our tests of quantum mechanics. It's our best probe for certain kinds of new physics. And like we said, it could spark completely new ideas for quantum tech, even if indirectly.
Okay, so let's try to wrap this up. The top quark. It's fundamental. Unbelievably massive, gone in a flash. Crucial for the standard model, the Higgs, but also maybe pointing beyond it.
Right. And while it won't be in your quantum computer, studying it gives us priceless insights into quantum field theory, high energy entanglement, and it might just inspire those future quantum sensors or computing ideas, maybe things like topological concepts.
And the research continues. At the LHC now, and maybe future colliders like the FCC, will reveal even more.
Looking for answers to those big questions. Baryogenesis, dark matter links, nailing down those entanglement details.
So maybe a final thought for everyone listening. Isn't it amazing how this particle, one of the heaviest things we know, existing for practically no time at all, how it holds clues to mass itself, the early universe, why matter dominates, and maybe even inspires future tech?
And all these fascinating ideas really came into focus through our deep dive into that essay by Yorgo Schnippat.
Thank you for joining us for this deep dive.
Goodbye.